in year n, the 300th day of the year is Tuesday. In year n plus 1, the 200th day of the year is also Tuesday. On what day of the week did the 100th day of year n minus 1 occur? So the first thing I'm going to do is draw out a little bit of a calendar for this question. And let's start filling in our values. So the first thing they tell you is that in year n, the 300th day is a Tuesday. So the 300th day is this Tuesday. And we have to kind of work from there. So therefore, 301 is Wednesday, 302 is Thursday, 303 is Friday, and so on, right? Like that. But obviously, we're not going to plug them all in. We can go and keep adding sevens, because every 7 days it's going to be a Tuesday. So if we do that, you can easily do that in your calculator. Just type in +7 and just keep hitting equals. It'll get to 363. So that means the 364th day is a Wednesday, 365th day is a Thursday. And then after that, we get into the next year, which is year n plus 1. 2, 3, 4, like that. 5, 6, 7, 8, 9. Now, of course, we don't have to keep doing this. We just want to get to day number 200 and ensure that it is indeed a Tuesday. So similarly, you can just keep adding 7 to this 8 here. And if you do that, you'll eventually get to ... 197. And therefore, this is 198. And this is 199. And then therefore, this is 200. So the 200th day is a Monday. But the question told you that the 200th day is Tuesday. So what happened here? What did I do wrong? Well, I didn't do anything wrong. I just wrote 365. The only way this can work is if we have one additional day. That means that year n is a leap year. And as you know, leap years have 366 days. So everything gets shifted over. This is now 366, and this is now 1. And you see what happened? And that is how we can make this question work. This becomes 7, this becomes 8, and so on. And then therefore, if we keep adding, this becomes 197, this becomes 198, this becomes 199, and finally our 200th day is indeed a Tuesday. All right? So that's the first part of the question. Now we got the second part of the question, which is what day of the week is the 100th day of year n minus 1? All right, so now we got to go backwards. Well, the good news is that year n is a leap year, so year n minus 1 is not a leap year, right? Because leap years come every 4 years, not a leap year. So n minus 1 has a standard 365 days, okay? So now we got to work backwards from 300. And similarly, if you just keep going backwards from 300, you, by a fact multiples of 7, you'll eventually get, 293, and so on, ... like that. You can do it in your calculator. You can subtract by 70 too to speed up the process. And if you do that, you'll get down to 13, and then you'll get to 6. So then you'll have 5, 4, 3, 2, and 1. And therefore, the Wednesday will be 365 of year n minus 1. But they want the 100th day. All right? So same thing. You got to keep going backward from 365. And you can always subtract by 70s. And if you do, you'll get all the way down to 106. All right? So you got 105, 104, 103, 102, 101, and finally 100. And that 100th day is a Thursday. So the answer to 25 is A. How many positive integers not exceeding 2001 are multiples of 3 or 4 but not 5? Okay, so we have 2001. When you divide by 3, it'll give you the number of multiples of 3, and that is 667, the closest integer value. 2001 divided by 3 is actually exactly equal to 667. And then now 2001 divided by 4 is a little more than 500, but we are looking for the number of multiples, so we're obviously going to be looking for just the integer values. So this represents the number of multiples of 3, and this represents the number of multiples of 4 between 1 and 2001. So this looks like a total of 667 plus 500. But there's a problem that we have counted a few of these twice. Which ones? Multiples of 3 times 4, which is 12. Multiples of 12 have been counted twice. So how many multiples of 12 are there, first of all? Well, same kind of scenario, 2001 divided by 12, and you take the integer value that's closest to that, and that is 166. So now the total number of integers that are multiples of 3 or 4 from 1 to 2001 is 667 plus 500, and we have to subtract the 166 that was counted twice. So therefore this is 1001 unique multiples of 3 and 4. All right, so now we've got the first part. Now we have to look at not multiples of 5. So of all of these numbers that we got, we have to take out the ones that are multiples of 5. So how do we do that? So of all the multiples of 3 and 4, we must now remove those that are multiples of 5. So let's start with numbers that are multiples of 3 and 5. And those numbers, since they are multiples of 3 and 5, they are multiples of 15. So, very similarly, you take 2001 divided by 15 and take the integer value of that, and you get 133. That's how many numbers between 1 and 2001 are multiples of 15. So these are the bad guys. Now we have to figure out how many are multiples of 4 and 5. Remember, of all the ones that we figured out in the first part of the question, we have to now get rid of the ones that are also multiples of 5. Well, multiples of 4 and 15 are multiples of 20. So these are the ones that we have to get rid of. Of all the ones from 1 to 2001, you get rid of the ones that are multiples of 20, and this is about 100. So now, very similarly, like we did earlier, we have to get rid of doubles because we've overcounted some of these. Which ones have we overcounted? The ones that are multiples of 3, 4, and 5. So if you have a number that's a multiple of 3 and a multiple of 4 and a multiple of 5, that has been overcounted. So that essentially means multiples of 3 times 4 times 5, which is 60, have been counted twice. So we got to get rid of those. So that's going to be 2001 divided by 60. Take the integer value, and that gives you 33. So now finally we have 133, 133. So 133 plus 100, but then we have to subtract the multiples of 60 that were counted twice, and it gives you 200. This represents the unique multiples of 3 and 5 and the unique multiples of 4 and 5. So these are the ones that we need to remove. Remove from what? Our original list, which was 1001. So, final grand finale of this question is you take the original list, which was multiples of 3 and multiples of 4, and subtract from it all of those numbers that are also multiples of 5. And therefore, the final answer is 801. And that would be choice B. In trapezoid ABCD, the bases AB and CD are labeled. We have AB is equal to 52 and BC is 12. CD is 39 and DA is 5. The area of ABCD is. Okay. So do you remember how to figure out the area of a trapezoid? If you have a trapezoid like this, and this is A, and this is B, and this is the height, the area of a trapezoid is A plus B divided by 2 multiplied by the height. Okay, so I think we have a lot of the information already. So that's pretty helpful. We just have to figure out, I think, the height, and then we'll be set. So I'll draw two perpendiculars like that, and those perpendiculars, of course, represent the height, h. And I think, well, let's make this a little bit bigger here. Yeah, like that. And then this part here, from here to here, is 39, right? Because it's the exact same as the top. So that means that this part and this part have to be 52 minus 39. So I'll call this part x and this part y. And therefore, x plus y has to equal 52 minus 39, which is 13. Right? So that's the first part. And anything else that they give us? I think that's it. I mean, we've labeled everything else. So this area formula, a plus b over 2 times h, we have a lot of this. A is 39 in our trapezoid. B is 52 all over 2 times h. So if we can figure out h, we'll be able to figure this out. So 39 plus 2 divided by 2 is 45.5 times h. So we'll just use this to figure out h right here. Okay, so now I immediately see, as I'm sure you do, a lot of Pythagorean relationships between those two right triangles. So for the first one, you got x squared plus h squared is equal to 25, correct? And from the second one, this guy here, we've got h squared plus y squared is equal to 144, 12 squared, y squared, sorry. And we know from here that x plus y is 13, so I can substitute that into here instead of having it in terms of y. I can put it in terms of x. So h squared plus 13 minus x, which is what y is, squared is equal to 144, like that. And I think at this point we can just solve this. So in the first one, we get h squared is equal to 25 minus x squared. In the second one, we get h squared is equal to 144 minus 13 minus x squared, like that. And therefore, since these two are the same, we can set them equal to each other, like this. 144 minus, let's solve this out, 169 minus 26x plus x squared. And then this becomes 144 minus 169 plus 26x minus x squared, like that. And then the minus x squareds cancel on both sides, and therefore we can put all the numbers on one side. So 25 minus 144 plus 169, like that. So this becomes 50, 26x, and therefore x is 50 over 26. All right, and I think we're very close to figuring out h. We can use this formula right there. X squared plus h squared is equal to 25. X squared, we know, is 50 over 26 squared, like this. And therefore this becomes approximately 25 minus 3.698. And therefore, if you do the math, you'll get h is equal to approximately 4.615. All right, so we got a lot of numbers here. Let's isolate this guy here. And we can finally solve for the area. 45.5 times h. H is 4.615. And this will be approximately 210. And therefore the answer will be, for number 25, C. Let n be a 5-digit number and let q and r be the quotient and the remainder, respectively, when n is divided by 100. For how many values of n is q plus r divisible by 11? So we have n, and it's a 5-digit number, like that, right? It's between, obviously, 99999. That's the largest 5-digit number, and the smallest is 1000. All right? That's their introduction to n. And they tell you that when n is divisible by 100, you get a quotient of q and a remainder. That's what is in the question. I think that's all they give you. And they also tell you that q plus r has to be divisible by 11, or at least that's what they want. So if q plus r is divisible by 11, basically what that means is that it will equal some integer. So k is an integer. So that means q plus r is equal to 11k. And I think that's it. That's all they give us. N will be equal to 100q plus r. Correct? Because remember, r is the remainder. So don't get confused by writing in 100r. So at this point, I'm going to split this up a bit. I'm going to split it up into q plus r, and I'm going to put the 99q over here. And the reason I did that is because q plus r, we have some representation. We have 11k, and that's 99q. All right? And the good news is that 11 factors from both of these, k and 9q, like that. And then we can put the 11 underneath the n, like this. And since k is an integer and q is an integer, that means that n is divisible by 11. So we concluded that n is divisible by 11. So all we have to do now is find the number of possibilities between 10,000 and 99999 inclusive that are divisible by 11. So how do you do that? You take 9999 divided by 11, and you take the integer value. That's what this symbol means. And that will give you all the numbers that are divisible by 11 from 1 to 99999. But we only want from 10,000. So you have to subtract it from that, all the ones that are from 1 to 10,000 divisible by 11. So this would be basically how you did that. And this gives you numbers of 9090 and 909. And if you do that subtraction, you'll get 8181. That is how many numbers that are between 10,000 and 99999 inclusive, 5-digit numbers, that When you divide by 100, give Q and R as the quotient and remainder, and the quotient and the remainder, when added together, are divisible by 11. So the answer to number 25 is B. Three mutually tangent spheres of radius 1 rest on a horizontal plane. A sphere of radius 2 rests on them. What is the distance from the plane to the top of the larger sphere? So this is the kind of situation we have. The only difference is that in our question, the three spheres that are on the bottom definitely would look something like that. And each of them has a radius of 1, so they're all equal. Now the sphere that's placed on top of them in this diagram is also equal, right? But in our question, it's not. It's a much bigger sphere. It's basically double the radius. But that's not a problem. It's not going to affect our diagram. Our diagram that we have here is going to help us regardless of what the radius values are. So first I want you to look at this initial diagram right here. Those dots right here, right here, right here represent the centers of those spheres. And when you join them, they form an equilateral triangle, correct? And that equilateral triangle basically has side length of what in terms of numbers? Well, the radius of each sphere is 1. So if you draw a line from the center of one to another, that's 2 radii. So each of those sides will be 2, like that. Sides of the equilateral triangle. Now what you do is you draw a diagram like this, which represents that sphere that's placed on top. And they want you to figure out the distance from the top all the way down to the bottom, like that. Well, how do you do that? You split it up into 3 segments. The first segment is from the middle of the top sphere to the very top, like that. The next is from the middle of one of the bottom spheres to the bottom, like that. And then the last component is going to be the one that we concentrate on the most in this question, which is from the middle of the top sphere down to the base of that triangle. Okay? Like that. Now, if we do that and we add up those 3, that will be the height of the total figure. Now, it takes a little bit of visualization. I know it doesn't look exactly like you think because this is 3D. You've got to basically visualize this in 3D. Now, the good news is the first one, which is from here to here, that's straightforward. That is the radius of the big circle. So that is equal to 2, as they state in the question. The next one, which is from here to here, basically it's from the base of that triangle, this triangle, from that triangle to the bottom, is the radius of one of the smaller spheres on the bottom, and that's 1. So this guy is equal to 1. And now we just have to concentrate on this one in the middle here, and that basically represents the distance from the center of the top sphere to the base of that equilateral triangle. Okay? And that one I'll call it H. So when I'm done, my total height from top to bottom of this figure will be this guy here, which is 2, plus my H, plus that one right there, 1. So it'll be 3 plus H. And you can see some of the answer choices, they're already in that form, 3 plus something. Almost all of them except this one. Well, perhaps that's 3 plus something also, maybe. All right, no problem. Let's proceed with, the only thing we need to proceed with really is finding H. Now, to find H, how do I proceed there? What's the trick? What's the magic? Well, first and foremost, I'm going to draw one line from the bottom of H to one of the corners right here, like that. That creates a right triangle right here. Okay? And that is the triangle I'm going to work on. But I'm going to draw it here because the diagram is getting kind of messy here. So that triangle I'm going to draw right here. Now this top to bottom was h. How about this hypotenuse here? What is that? The good news is we know that. It's the distance from the center of the top sphere to the center of one of these smaller spheres. So that basically means it's just the two radii. When you draw a line from the center of the top sphere to the center of the bottom sphere and connect them, it'll be equal to 2 times the radii. The radii of the top sphere, which is 2, and the radii of one of the bottom sphere, which is 1. So this will be 2 plus 1, like that, which is equal to 3. And now I just need to figure out this side right here, x. If I can figure that out, I'm set. I can figure out h, and then I'm done with the question. To do that, I have to concentrate on this equilateral triangle. And I'm going to draw that equilateral triangle over on the side here. So there you have it. That's your equilateral triangle. And I want you to try to figure out, where is it that this height touches that base? Where does the height meet the plane of that equilateral triangle? Well, that's why I drew it bigger, because it will definitely help if I explain it on a surface where you're looking head on. So I've drawn out this equilateral triangle that basically represents this one right there. But now we're looking at it head on. If you draw lines from the vertices to the opposite sides, like that, where they all meet is the center point. And that center point is basically right there. That is where the height will touch that equilateral triangle. Okay? So basically what we need to do is we need to figure out this x, right? This x in this diagram is represented by the green line right there. This one right there. But what about in my diagram here? Where's that x? Well, I could draw it in several places really, but it really is a vertice of the equilateral triangle connected to the center. So it basically would be right here, from here to there. That would be x. Okay? Now we get into the angles of this triangle. This is an equilateral triangle, right? So that means that these are all 60 degrees. So since these lines that I drew cut those angles in half, this is 30 degrees right here. This is a right angle, and therefore this would be 60, because the angles have to add up to 180. And since this is a 60, 30, 90 triangle, we know that the ratio of the sides are 1, 2, and root 3. Correct? This side is going to have a ratio of 1 to 2 for that side, and this side will have a ratio of 3. Now, do we know the length of any of these sides? We do, because the equilateral triangle, remember, has a side length of 2. So from here to here, right here, that's half of the side, correct? So that will basically would be 1. So there we go. We have now enough to figure out x. X over 1 in terms of a ratio would be 2 over root 3. This guy right here. So you see how the ratio of the sides of a 30, 60, 90 triangle help us out. And therefore x is just 2 over root 3. So there we go. We've got everything we need to figure out h. Using that triangle and Pythagorean theorem, we have x squared plus h squared is equal to 3 squared. X is 2 over root 3, all squared, plus h squared is equal to 9. And therefore h squared is equal to 9 minus 4 over 3. And if you get a common denominator, you'll get 27 over 3 minus 4 would be 23 over 3. And therefore h would be equal to the square root of 23 over 3. All right? So therefore my total height finally is 3 plus h, and h is 23 over 3, the square root. So let's see, any of our answer choices match that? At first glance, they don't. And this is another example of something like that happening, where you get the correct answer, but it's not one of the answer choices, or it doesn't look like one of the answer choices. So we have to somehow manipulate our answer, not in a way to make it look like it, but we have to basically put it in a different form. And I think what they did is they just rationalized the denominator. So this is 23 root over root 3. So they multiplied top and bottom by root 3, like that. And if you do that, you basically get 3 plus 23 times 3 is 69, which is root 69. And then root 3 times root 3 is 3. So 3 plus 69 over root 69 over 3, so that would be b. So what I really meant to say was that once you get an answer, say, of this form, obviously you can't add 1 to it, or add something. You can't make it a different value than what it is. But you can make it in a different format to make it look exactly like one of the answer choices. And in our case, we did that by rationalizing the denominator. So there you have it. Number 25, the answer is B. In triangle ABC, we have AB equal to 25, BC is 39, and AC is 42. Points D and E are on AB and AC respectively, with AD equal to 19 and AE equals 14. What is the ratio of the area of triangle ADE to the area of quadrilateral BCED? So first, let's draw our diagram. Let's say we've got some triangle in here. We don't know exactly what it looks like, but let's say it looks something like this. And let's start labeling our sides. A, B, and C. And they're saying this is 25, this is 42, and this is 39. And some point on here is D, AB, and some point on AC is E. So this is E, and this is D. And they're going to draw a line from D to E like this. And they want you to figure out, in the end, a ratio between triangle ADE over the quadrilateral BCED, like that. Well, I immediately noticed that if you have a quadrilateral BCED, that's basically the full triangle ABC minus ADE. Correct? All right. Okay, so how do we do this? Well, they gave you some clues here. AD, that's going to help us tremendously, I think. AD is equal to 19, and AE is equal to 14. So I can fill in the other side, since it's 25 here, the whole side. This is going to be 6 from D to B, and E to C is going to be 28. Okay. All right, here we go. Now the first thing I want to do is I want to draw a little bit of a line segment that's going to help me. And that's from B to E, like this. Okay, I think I have everything I need to move forward. Here we go. The first thing is looking at triangles ADE and ABE. Now I want you to understand this, so I'm going to draw a height to show you how this can be arranged. This is my height, my perpendicular distance from E to the base, and I'll call that H1. Okay, H1. Now, let's figure out the area. ADE, 1/2 base. What is the base of AD? It's 19, correct? Times height, well, the height I just drew, H1, all over ABE. ABE, the base is 25, 1/2 times 25, and it has the same height. So this just boils down to 19 over 25. All right? And in a very similar way, I will compare ABE to the full ABC. And before that, I do that, I will draw a very similar type of height from B down to the bottom to make that a perpendicular. Okay, I'll call that H2. Okay, so ABE, the base is 14, 1/2 base times height. Height is H2. ABC, the base is 42, 1/2 base times height, and the height is H2. So in a very similar way, we get 14 over 42. All right, which is, I think that's 1/3, right? Yeah. Okay, great. So now we can look at ADE and ABC. And that's very helpful because that's the triangles that are in our big ratio that we have to find. Well, I'm going to use what I just figured out. AD over ABC is essentially ADE over ABE times ABE over ABC. Correct? Because these two will cancel. And this guy I already know is right here, 19 over 25. And this value I also know is 1/3. So there you have it. We got 19 over 75. And now we can solve for our ratio. So the ratio that I want is ADE over ABC minus ADE, like that. Now what I'm going to do is I'm going to flip this. It makes it a little bit easier for me. If I do that, watch what happens. I get ABC minus ADE over ADE, like that. And this helps a lot because 1 over R now becomes just ABC over ADE minus 1. See how that helped there? So ADE over ABC I just got was 19 over 75. So that means 1 over R is equal to ABE over ABC is 19 over 75. So if you flip it like that, it's actually 75 over 19 minus 1. So 1 over R is therefore 75. Get a common denominator here, 19, 19. 75 minus 19 over 19, which is 56. And therefore, the final step is you got to flip it to get R. And that's 19 over 56. R, of course, being our ratio. And there you have it. That's the answer. So number 25, 19 over 56, is D. A bug starts at one vertex of a cube and moves along the edges of the cube according to the following rule. At each vertex, the bug will choose to travel along one of the 3 edges emanating from that vertex. Each edge has equal probability of being chosen, and all choices are independent. What is the probability that after 7 moves, the bug will have visited every vertex exactly once? So let's draw a cube. So here's a cube, and let's label it. Let's label the vertices. Let's just give them letters: A, B, C, D, H, E, F, G, H. So like that. And let's start discussing this question. So we're going to start, of course, at A. And from A, we have 3 possible ways of going. We can only go to a vertex that's, attached to the original point. They explained that in the question. So from A, I can either go to B, I can either go to C, or I can go to D. So from A, I can either go to B, C, or D. Okay? So that gives me 3 possible choices. Now I'm going to choose one of them to kind of explain this, but the explanation, it holds true for every other possibility. From A, let's say I chose to go to B. So I was here, now I'm here. Now once I get to B, where can I go? I can't go back to A, because if I did, there's no way I can reach all of the vertices. I can only go to either C or F. So that means from B, I've got only 2 choices, either C or F. So my number of choices is 2. And then let's say I go to C. From C, where can I go? Well, at this point, the choices narrow down pretty quickly. I can only go to G here, or I can go to D right there. Now, when I get to G, there's only one possible path at that point. It's F, E, H, D. F, E, H, D. If I do that, I will reach all the vertices in 7 moves. All right? Now, when I go to D, let's say I chose to go to D here. So now I'm going here. If I go there, then I've got 2 possible ways of moving in order to reach all the vertices. One path is H, E, F, G, and the other path is H, G, F, E. So as you can see from C, there's really only 1, 2, and 3. 3 possible paths. And now what you do is you multiply them. We have 3 up here, we have 2 there, 3 here. So the total would be 3 times 2 times 3, which is equal to 18. 18 possible ways that I can reach all 7 vertices with 7 moves. Now this question is a probability question, so that means I've got to figure out a numerator and a denominator. The numerator is what I actually just did there. Now the denominator is the total number of moves. The total is going to be as follows. There's 7 moves, right? 1, 2, 3, 4, 5, 6, 7. And each move, you've got 3 possible choices. Like if you start at A, at the very beginning, you can go to B, C, or D. And then when you get to B, you can go either A, C, or F, right? This is the total possible, regardless of our outcome. So for each of these, it's 3. Every time you get to a vertex, there's 3 ways you can move, according to the question stem rules. So that is essentially 3 to the power of 7. So there you go. That's our probability. Now, of course, we got to get this into a fraction.
So that is equal to 18 over 3 to the power of 7, which is 2187. And then 18 over 2187, I believe you would have to divide by 9 to get this in lowest terms. And if you do, you get 2 over 243. So there you go. Number 25, the answer is C. For each positive integer n, let Sn denote the sum of the digits of n. For how many values of n is n plus Sn plus S of Sn equal to 2007? Several approaches to this question, and I'll just go systematically without anything too fancy. First and foremost, what I want to know is how many digits are there in S. That will help me create a certain range, because otherwise there's way too many values for me to look through. I don't think it's 1 digit or 2 digits. Probably got to be at least 3 digits. So what is my largest 3-digit number? It's 999. Let's see if this even comes close. N plus Sn, like this, plus the S of Sn, and that's got to be 2007. Well, n is 999 plus Sn, the sum of the digits of 999, which is 27, plus the sum of the digits now of 27, that's what this means. So that would be 9, and that is equal to 1035. So I fall quite short of 2007. So that means n must be 4 digits. It must be a 4-digit number. Okay? Now, one thing for sure is that n has to be less than 2007, right? Because think about it. If it's 2007, it would be 2007 here, plus the sum of the digits of 2007, which is 9, plus the sum of the digits of this, which is another 9, and that's obviously going to be greater than 2007. It's going to be 2025. So n has to be less than 2007. So my range for n is less than 2007, but greater than 1,000, right? Because it's got to be a 4-digit number. Now that's a very big range, and I certainly don't have time to go through every single value, nor would you want to do that. But I can do a little bit of experimentation and break this down into some cases. And the first is if n is greater than or equal to 2,000, and then I'll look at values that are very close to 2,000 but are less than 2,000, like that. So let's look at this one first. If it's 2,000, and we can do this pretty quickly, 2,000 using this formula right here. 2,000, sum of the digits of 2,000 is 2, and sum of the digits again of that is 2, and that gives me 2004. Okay, not 2007, but it's pretty close. How about if I chose 2001? Sum of the digits of that is 3, sum of the digits of 3 is just 3, and there you go, that is 2007. So I just got one value that works. So it's got to be at least 1, so we got 1. Now, we want to do this quickly, right? It's a math contest. We don't have all day. We've got probably 3 minutes. So in a very quick way, we want to see if this trend is going to continue. 2002 plus 4 plus 4. Ooh, this is going to be way over. Well, not way over, but it's actually 2010. So that's it. For this, we are done. We don't need to look at any more values. All right. Now let's turn our attention to this guy. Less than 2,000. All right, let's do this quickly. 1999. Let's start with that and keep going. Let's see. Sum of the digits 27 plus 1, 28. And then the sum of the digits of 28 is 10. And this looks like it's 2037. Okay, it's not 2007, but that's okay. Now, instead of going down every one, 1998, 1997, that's going to take forever. I'm going to go down by tens. So this one gives me 19 plus 10, and that is 2019. All right, I'm going in the right direction here. I'm getting closer to 2007. Let's go down by 10 again, 1980. This is 18 plus 9, and that is 2007. Look at that. So we got another one. Great. Let's keep going here. Let's try 1970. That gives me 17 plus 8, and that is 1995. Okay, so we've gone lower, so that's it. Now, it's tempting to just say, okay, there's probably only two. Let's choose B and move on, or end. That's the final question on the contest. But the answer choices are actually 2, 3, 4, 5. They're going all the way up to 5. So that makes me think that there might be a couple more. So what I'm going to do is very quickly hover just around 1980. And that's all I'm going to do is just look at the very vicinity of 1980. Because once I get up to 1990, we're going to 2019 and we're getting much bigger. And once I go down to 1970, we're getting smaller. So let's start with 1981. Let's see what we get. This becomes 1 plus 9, 10. 10 plus 9, 19. 19, 9 plus 1 is 10. And that is 2010. Let's try 1982. That is going to be 20 plus 2. And that looks like 2004. Let's try 1983. That looks like 21 plus 3. And that is indeed 2007. So there we go. We just got another one, 1980. And let's go in the other direction, because I don't think this is going to keep helping us if we go greater than 1983. Let's go in the other direction. So 1979, that's going to give me 26 and 8, and that sum is 2013. Let's try 1978. That gives me 10 plus 15, which is 25, and then 25 gives me 7. So 1978 plus 25 plus 7 is 2010. All right, let's try 1977. That gives me 10 plus 14, which is 24. 24, sum of the digits is 6. So 1977 plus 24 plus 6, and that is 2007. Great. So we got another one. And the good news is that those are the only ones. 2001, 1980, 1983, and 1977. And the answer to this question, therefore, is 4. A round table has a radius of 4. 6 rectangular placemats are placed on the table. Each placemat has a width of 1 and length x as shown. They are positioned so that each mat has 2 corners on the edge of the table, these 2 corners being endpoints of the same side of length x. Further, the mats are positioned so that the inner corners each touch an inner corner of an adjacent mat. What is x? So a little bit of labeling, of course. I'm going to first connect all of these guys. And this looks like a 6-sided shape. 1, 2, 3, 4, 5, 6. And therefore, all of these angles inside are 60 degrees. That's 60, that's 60, and so on, all the way around. Now, what's interesting is that when you draw these lines, you'll notice that each of these lines is the same. That's the same in terms of length to that line. So that means this is isosceles. If it's isosceles, that means these two angles are the same. So 180 minus 60, which is 120, is going to be equal to 2x. So that means this is 60, and that's 60, like that. So these are all equilateral triangles, basically. That's 60, and so on. So that's the first part of this question. Now I'm going to draw a few very important and helpful clues. The first is from this point right here to that point right there. The next is this segment, which essentially represents x, and then I'm going to connect that right back to where I started, like that. Okay, and I think that should be sufficient. So let's label this now. This point down here I'll call R, this point up here I'll call P, and this point here I'll call Q. And this is 90 degrees because that's part of a rectangle. So a few things that we need to write out that the question actually gave us. They told us that the radius is 4. Now the line PR that I wrote goes through the center, and therefore it represents the diameter. So PR is 8. All right? And then PQ is equivalent to our x, which is what we have to solve for in this question. So immediately in this right triangle, PQR, I know that PQ is x, and PR I actually have the numerical value of 8. So now, of course, I have to concentrate on RQ. Well, RQ, part of it we know. We know this guy right here, this little distance there. They told us that is 1. So this is 1. I'll squeeze that in there. That's 1. Now I need to figure out the distance from here to here. If I can do that, I shall be able to use Pythagoras. Well, the good news is this little guy in there we also know is 1. Okay? So I guess now we just have to figure out from there to there. And we can label those 2 points if you really want to. We can call this point and this point, we can call them S and T. So this is S, this point right here, and this point right here we can call T. Okay, now take a look at this triangle right here, this one. That triangle you can clearly see, because this is x and this is x, that triangle is isosceles. And therefore this angle and this angle are the same. Now this whole thing is 120, so therefore this angle is 30 and this angle is 30, like that. What I'm going to do is just look at this triangle right here. I'm going to actually draw it out here to avoid making this diagram too messy. And there you go. That's that triangle, 30, 90, and 60. And this side is x. And this is what we're going to use to figure out the distance from S to T. This side here, I don't know what it is, so I'll just call it ST over 2, which is basically what it is. And now 30, 60, 90, the ratio of the sides are 1, 2, and root 3. So we can use that to figure out ST. ST over 2 over x is equivalent to root 3 over 2. So that means ST over 2 is equal to root 3 over 2x, and therefore ST is equal to root 3x. And there we go. So now we've got a Pythagorean relationship with triangle PQR, and that is as follows: PQ squared plus QR squared is equal to PR squared. PQ is x. QR, okay, QR is first, you got this distance, which is 1. Then we got from S to T, which is root 3x. And then we've got this little guy here from T to R, which is 1. And all of that squared. And then PR is just 8. So this is the equation we have to solve. So we've got x squared plus root 3x plus 2 all squared is equal to 8 squared, which is 64. So this is x squared plus 3x squared plus 4 root 3x plus 4 is equal to 64. Bring everything over on one side, collect like terms. 4x squared plus 4 root 3x minus 60 divided by 4. We'll get rid of a lot of 4's. And we just get left with x squared plus root 3x minus 15. And this is most likely going to need a quadratic to solve. So we got x is equal to minus root 3 plus or minus the square root of root 3 squared minus 4 times 1 times negative 15 all over 2a. And this looks like minus root 3 plus or minus 3 plus 60, so root 63 all over 2. Now x is a distance, so it's most likely minus root 3 plus root 63 over 2. And I think we can simplify the root 63. It's 9 times 7, so 3 root 7 all over 2. So there you go. Minus root 3 plus 3 root 7 over 2. Minus root 3 plus 3 root 7 over 2. And that is choice C for number 25. For k greater than 0, let ik be 10.064 where there are k zeros between the 1 and the 6. Let nk be the number of factors of 2 in the prime factorization of ik. What is the maximum value of nk? So, if you have any number and you divide by 2 and it ends in 64, there's a couple different scenarios. The first scenario is, let's just look at 64 itself. If you divide by 2, you get 32, then 16, then 8, then 4, then 2, then 1. So how many times was I able to divide by 2? 1, 2, 3, 4, 5, 6, right? And therefore 64 is equal to 2 to the power of 6. Now I can't keep going here because if I divide 1 by 2, I get a decimal. And that's not allowed because we can't do that with factors. So that means it looks like 6 is the only way, no matter what the number is. But there's one other scenario when you have very large numbers. And that is, you can have some big large number, let's say 1000064. And this number has a unique property as follows. If you take this number and start dividing by 2, you will get pretty much the same kind of story as this one. You get 32, you'll get 16. I'm just writing out the last 2 digits. You'll get 08, you'll get 04, and then you'll get 52. And interestingly, 52 is divisible by 2. 26 is what you get. You notice how we don't get a 1. And then what that allows me to do is go one more further into 13. So now I've got 1, 2, 3, 4, 5, 6, 7 times. So this number is 2 to the power of 7 times something. I think it's 2 to the power of 7 times 7813, I believe. So as you can see, this was the key right here. It allowed me to go one step further. Normally when you divide by 2, you get 1. But if you have something like 52, or if you had 12 and you divide by 2, you get a 6. And like I did here, and that 6 allows me to go one step further. And this is indeed the maximum, because there's no way that you can have anything more than 7 in terms of the number of factors of any number of this form, where you have 1 followed by a bunch of zeros and then 6, 4. So number 25, the answer is B. Jim starts with a positive integer n and creates a sequence of numbers. Each successive number is obtained by subtracting the largest possible integer square less than or equal to the current number until 0 is reached. For example, if Jim starts with n equals 55, then his sequence contains 5 numbers. 55 minus 7 squared, then that's 6. Then 6 minus 2 squared, which is 2. 2 minus 1 squared, which is 1. And then 1 minus 1 squared, which is 0. Let n be the smallest number for which Jim's sequence has 8 numbers. What is the units digit of n? This question, the general rule is that you're taking some number and you are going to add to it some square. And that must be less than n plus 1 squared. So for example, when we had 6 as our a, we had to add this 7 squared, right, in order to get 55. And when we did, you got 49 plus 6, which is 55. And 55 is less than n plus 1 squared, which would be 64. So that's the only way this can work. So we have to apply this general rule. But we have to go in reverse. And that will allow us to figure this out. So I have to have 8 numbers. So I've got to go from A8 all the way back to A1. So A8 all the way back to A1, A7, A6, A5, A4, A3, A2, and A1. And A1 is what I'm interested in. That is the number that is our n, I guess. So the only way we can do this without an enormous amount of guessing is to fully understand the general rule. So this is our general rule. This was just an example. So that means a plus n squared is less than n squared plus 2n plus 1. The n squareds cancel, so that means a is less than 2n plus 1. And therefore n, if you isolate for it, it would be a minus 1 over 2. That n is greater than. So let's work with this. We have to end with the 0, right? That's the criteria. Until 0 is reached. So my A8 has to be a 0. Now we start employing this rule. How do we get to a 0? Well, just as before, we had to have taken 1 and subtract from it 1 squared in order to get 0. They even give you that up here. So it kind of helps you out a little bit. Okay, no problem. How about A7? Well, A7 obviously was 1. Okay, and how do we get that? Well, we just did the same thing they did up here. 2 minus 1 squared. So that the first few are pretty straightforward to get 1. Okay. Now, what will be my A6? Well, the A6 is right here. That's A6. How did I get that, though? Well, how did I get A6? Well, I think I can get that pretty straightforward, in a straightforward way, by just going 3 minus 1 squared. So far, its numbers are pretty small. So that means that my A5 is 3. Now, at this point, we can continue to do it in terms of inspection, but since the numbers are getting a little bit larger, I'd like to apply this formula. I didn't think we really needed it until now. Now, this number represents my A. And this square that I'm going to put in here, like I had done up here, that's going to represent my n. So this formula allows me to figure out what I can make my n. If a is 3, it would be 3 minus 1 over 2 has got to be less than n. So this gives me 3 minus 1, which is 2. 2 divided by 2 is 1. So my n has got to be greater than 1. And I've got to choose the smallest possible. So the smallest possible is 2. So there we go. 2 squared. And therefore this number, subtract 2 squared, has to be 3. And that means this number is a 7. So you see how he got that? So that means A4 is 7. Now, how did I get a 7? Well, we go back and we apply this formula right here. This is my A, and I had to have some sort of n in there. What is n? Well, a minus 1 over 2 is less than n, so that would be 7 minus 1 over 2 is less than n. That means 3 is less than n. So the smallest possible value for n is a 4. That's what goes there. So 7 plus 4 squared would be the number that goes in here, and that is 23. Okay? So now that the numbers are getting larger, it gets more difficult. So that means A3 is 23, but how did I get 23? And that's where this comes in yet again. A this time is 23, so 23 minus 1 divided by 2 is less than n. So that means n has to be greater than, that looks like 11. So I'll choose 12. That's the smallest number I can choose for my n. So this number, subtract 144 is 12, and if you do the math, you'll figure out that number is 167. So this A2 is 167. So we're down to our final step. How do we get 167? Apply this formula one last time. A in this case is 167 minus 1 all over 2 is less than n. That means n is greater than 166 divided by 2, which is 83. N has to be greater than that. So the smallest I can make n is 84. So this number, subtract 84 squared, is equal to 167. And that number, if you do the math, is 7223. So that is my A1. That's the number that I start with. And they want you to figure out the units digit of this number, and the units digit is 3. So number 25, the answer is B. Let R be the square region with n greater than or equal to 4, an integer. A point x in the interior of R is called n-ray partitional if there are n rays emanating from x that divide R into n triangles of equal area. How many points are 100-ray partitional but not 60-ray partitional? Let's first discuss what this question means. So we'll draw a diagram. Here's a square. And what I'm going to do is putting it on a coordinate grid. And we'll just put some point we can call x. So right here, let's say that's x. And emanating from x, you're going to have these rays, right? And obviously these rays are emanating in such a way that they divide that square into a whole bunch of equal triangles. So some of those rays obviously will need to go through the vertices. So let's just draw those ones that go to the vertices like that. Then we've got another one going down here, and then another one going to that. Okay? Now, this one, of course, as you can clearly see, it divides it into 4 regions, and these 4 regions are not equal, but there's going to be a whole bunch of rays that emanate in order to make a whole bunch of equal segments. So that is the challenge of the question, right? I'm just, in a very sloppy way, sort of just showing you that all of those segments eventually are going to have equal value. But we don't know how many there are for the general case. We're given 2 cases, 60 and 100, but obviously we're not going to draw 100 of those emanating rays. That would be impossible on a diagram. So we have to talk about it in terms of general terms. So here we go. make things easy, let's put this on a coordinate grid, and let's call this 0, 0. Let's call this point 1, 0. This is 1, 1. And this is 0, 1. Okay? So first and foremost, x, I will give some sort of a coordinate. I'll call it AB. A on the x-axis and y on the B on the y-axis. So if I drop a perpendicular from that point x, and similarly if I extend it to the y-axis, those are obviously going to be labeled here as A and here on the y-axis as B. Okay? So now what we can do is we can label these 4 regions. This region right here, this guy, I will call R1. So I'll try not to make it confusing. And this region in here, I will call R2. This region here, I will call R3. And the last one, of course, this guy, I will call R4. So let's first calculate the area of all of these. R1 is 1/2 base times height. The base, of course, is just 1, and the height is B. So R1 is B over 2. R2, that is also 1/2 base times height. The base is 1, and the height is from here to here, which is 1 minus A. So that's 1 minus A over 2. R3 is this one, and this height is 1 minus B. So it basically becomes 1 minus B over 2. And finally R4, that's going to be A over 2 in terms of its area. All right. So we have to do a few things here. The first thing is, of course, to understand that R1, R2, R3, R4 are not equal. We have to divide them in a way so that every single divided segment is equal throughout the entire square. So let's now do those divisions. And this region, that's R1, I will divide that into N1 different segments. This region, R2, I'll divide into N2 different segments. This region, I'll divide into N3 different segments, and this region, N4. So essentially what that means is that you're going to draw N1 different emanating rays to cut that into equal segments. Okay, I don't know how many N, but N is obviously a lot. And in a very similar way, you have to do the same thing with R2. You have to draw N2 different lines. So whatever, if N2, let's say it was 20. And the goal, of course, is that, and it says in the question, that divide that square into triangles of equal area. So that's the goal. So we'll talk about this bit by bit to explain it. So that means once you cut all of those into segments, those segments are all equal. Okay? And that's very important to understand. So that means that B2, when it's divided by N1 segments, each of those segments is B2N in terms of its area. And then similarly, when you do that with R2, each of those segments is 1 over A over 2N2 in terms of its area. And then very similarly for R3, it's 1 over B 2N3. And then for R4, it's A over 2N4. So each of these is equal to each other. So all of these are equal. Okay, so I hope that makes sense. Now, since we've got this equality, let's use it. And in particular, let's use the ones that have the same variable, at least for A and B. So b over 2n plus 1, 2n1 is 1 minus b 2n3. And this will allow me to isolate for b. Cross multiply and you get 2. Actually, let's get rid of the 2's first. So I will only need to cross multiply b with n3. And then this will become n1 minus b n1. Put everything on one side and you get b n3 plus n1 all over is equal to n1. And therefore b is equal to n1 over n3 plus n1. Okay, so that's going to be very helpful for us. And in a very similar way, let's equate those two. And when you do, you get 1 minus a is over n2 is equal to a over n4, right? I just got rid of the 2's. And cross multiply a n2 is n4 minus n4a. And then bring the a's over and you get a n2 plus n4 is equal to n4. And then finally, a is equal to n4 over n2 plus n4. Okay, so far so good. I hope this you have been following without too much confusion. All right, now this is a very important part of the question. Look back up here, R1 and R3. If you were to add them, right, R1 plus R3, what do you get? You get b over 2 plus 1 minus b over 2, and that is equal to 1/2. Now the area of the entire square, it's a unit square, which is what I chose to make this easy in terms of the math, has an area of 1. So R1 plus R3 are essentially half the area. Very similarly, look at R2 plus R4. This and that. If you look at those and add them up, it's 1 minus a over 2 plus a over 2, and that is also a half. So that means those two regions comprise a half. And that's very important because that means that, and I'll try to explain this carefully, in R1 you have n1 triangles, right? Because n1 rays are going to be emanating from x, whatever n1 is. So you're going to have n1 triangles in R1. Similarly, for R3, you're going to have n3 triangles because you're going to have n3 rays emanating from x. And all of the triangles that make up R1 and R3 are given by this number, n1 plus n3. That is all the triangles that make up region R1 and R3. And all of those triangles add up to a half in terms of their area. Very similarly, for region R2 and R4, you have n2 plus n4 triangles. And remember, the question told you that all the triangles have equal area. And because they all have equal area, that means these two must be equal. Okay? That's a very important point in the question. I hope that I've explained that well. All right, so now we can proceed. We are told that we want to create 100 partitions. So that basically means that n1 plus n2 plus n3 plus n4 has to equal 100, right? 100 partitions for those 4 regions. Well, that's very helpful. And since n1 plus n3 is equal to n2 plus n4, right over here, that means that we can separate this, n1 plus n3 plus n2 plus n4 is equal to 100. And both of these are equal, right? According to this right here. So both of those, if they're equal, they must be equal to 50 each. So that's 50 and that's 50. Okay, so here we go. Let's keep that square in the diagram. So that means my x, which I had previously labeled as AB, and I had figured out that it was, if you remember here, B is n1 over n3 plus n1. And that basically means that it's going to be n1 over 50, since n3 plus n1 is 50. And A was n4 over n2 plus n4. That's basically n4 over 50, since n4 plus n2 is 50. So I've got n1 over 50 and n4 over 50 for my values of B and A. So that's n4 over 50 and n1 over 50. So what that means is that this is a fraction. So x can be anywhere from here to here, right? And for example, if n4 was 25, it would mean that this is 25 over 50, which is a half. So x would have an x coordinate of a half. Does that make sense? Or very similarly, let's say n1 is, say, 10. That would mean this would become 10 over 50, which is 1/5. That means x has a y coordinate of 1/5, which is approximately here. Okay? So this is very helpful at this point, because that means that n4 can be any integer from 1 to 49. The reason it has to be an integer is because n represents the number of emanating rays, right? It's the number of rays, so it has to be an integer. Why 1 to 49? Why not 1 to 50? Because if it's 50, then it would be right on this line. It would be 50 over 50, which is 1. And x is inside that square. Okay? So for n4, I have 1 to 49 choices. And for similarly, I also have 1 to 49 as my choices for the same reasons. So the number of ordered pairs, I guess, AB, are 49 possible ordered pairs for n4. Well, for 49 possible choices for n4 and 49 for n1. So 49 times 49, which is 2401, is the number of ordered pairs AB. Okay? But remember, this whole conversation is for 100 ray partitions. Okay? We want to compare it to 60 ray partitional. If you have 60 ray for the question, then it would essentially be identical in every way. The only difference is that when you get to the very end, your x would be some sort of m over 30 and some sort of m over 30, like that. Exactly how we got it up here. Everything else would be identical, except for instead of 50-50, it would be 30-30. And our question is saying, how many of these are not going to be like this? So let's compare these to these. Well, we want to compare n over 4 over 50 to m over 4, 30. And if you do the math there, you cross multiply, you get that m4 is 3 over 5 n4. So that means that for any of these values from 1 to 49, the only way you can get an integer for m4 is if the number that you put in for n4 is divisible by 5. So the only way you're going to get integer values for m4 is if you put values for n4 that are divisible by 5. So for example, m4 can only be a integer if you have the following values for n4. 5, 10, 15, 20, 25, 30,
35, 40, and 45. From 1 to 49, these are the only 9 values that will give a integer value. So for example, when n4 was say 20, this would be 20 divided by 4, 20 divided by 5, which is 4. 4 times 3 is 12. M4 would be 12. Okay? Does that make sense? So these are the ones that we cannot have because we don't want this to have any common with that. So first and foremost, how many are there? Well, there's 9 for n4. 9 for m4. 9 values. And very similarly, you'll get 9 for m1. So 9 times 9, which is 81, represents the number of ordered pairs of that form for a 60-ray partitional scenario. So from this 2401, these 81 I cannot have. So I have to subtract from 2401 those 81. So that's the final step to our question. 2401, subtract these 81, because I don't want these to be the same as this, and they will be the same when you have these 81 ordered pairs. And this number is 2320. And that is the answer to the question. 2320. Number 25 is choice C. Real numbers x, y, and z are chosen independently and at random from the interval 0 to n for some positive integer n. The probability that no two of x, y, and z are within 1 unit of each other is greater than a half. What is the smallest possible value of n? Well, we do not know the actual values, but we do know that they are most likely on some number line, and they are between 0 and n. And we can make x greater than y, or less than y, less than z. So I can put x here, y here, and z here. So our conditions, according to the question, are that x minus y, if you take the absolute value, the positive difference, has got to be greater than or equal to 1. That's what it means, that no two of x, y, and z are within 1 unit of each other. And then similarly, y minus z, the positive difference has got to be greater than or equal to 1, and so does x minus z. So those are our conditions. So really what we're just dealing with is, since we've set this inequality, x minus y is greater than or equal to 1, and y minus z is greater than or equal to 1. We can drop the absolute values, and then we don't need to worry about the other one, because as long as these are true, the other one will be true as well. Now the probability of that happening is greater than a half. So our task now is, how do we figure out the probability? What is the trick in this question? Well, what we have to do is we have to actually look at it from the angle of a cube and a tetrahedron within the cube. So I'll show you a diagram of what I mean. So here's a cube, and the red is basically the region that we have to consider first. And that first region is the denominator in the probability. So if the probability is considered, let's say, region 2 over region 1, this green is basically the region 1. Now, how do we figure out the area of region 1? Well, it's a tetrahedron, right? And the volume of a tetrahedron is 1/3 times the base times the height. Now, in this case, this cube is the full interval, 0 to n. So each of these sides is n. This is n, this is n, this is n. So the volume would be 1/3 times base, and the base is just this triangle. So the area of that base is pretty easy to figure out. It's just going to be 1/2 base times height. You can use this as the base, and you can use this as the height. So it's just going to be 1/2 n times n. The height of this tetrahedron is the top to bottom height right there, which is n. So this basically becomes n to the power of 3 over 6. So that is what is R1.
n to the power of 3 over 6. Now we have to figure out the R2, this guy. Well, how do we do that? Well, again, we're going to use a very similar technique. We are going to use another tetrahedron. And it's this one this time. And in particular, you have to look at the black lines. Those black lines represent the region 2 that's up here. And that one is very similar in terms of its shape. It's also a tetrahedron. And that volume is calculated in a very similar way. But we have to take into consideration that it's no longer n. Top to bottom is n, right? It's the same cube. But as you can see, the lengths are shorter. And the reason it's shorter is because that is 2, that distance. So that length of the black one is n minus 2 there. And then if you notice, this length is also shorter. That's also n minus 2. And this right here is also n minus 2. And those we deduce entirely from those inequalities right there. So the volume of that tetrahedron is 1/3 times the base, which is 1/2 base times height, which is n minus 2 squared, and then the height, which is n minus 2. So this just becomes n minus 2 all cubed over 6. So that's R2, so we put this over here, n minus 2 cubed all over 6, like that. So if you were to simplify this, this basically simplifies to n minus 2 over n all cubed. And we want this to be greater than 1/2. And we have to figure out what value of n would make that expression greater than 1/2. And if you start plugging in these numbers, you'll find that the first time this expression becomes greater than 1/2 is when n is equal to 10. When it is equal to 10, it becomes 512 over 1,000. And as you can clearly see, that is greater than 1/2. And the first time that happens, the smallest value for which that happens is when n equals 10. And therefore, number 25, the answer is D. All 20 diagonals are drawn in a regular octagon. At how many distinct points in the interior of the octagon, not on the boundary, do 2 or more diagonals intersect? Here is the non-scientific way. You just draw it. Draw your octagon, represented by this yellow boundary, 1, 2, 3, 4, 5, 6, 7, 8 sides, and then you just take your ruler, and I think rulers are allowed, I'm not really sure, but they should be, and just start drawing all the 20 diagonals. Shouldn't take that long to draw 20 lines. And then start counting all the intersection points. And the intersection points in this diagram represented by the red dots. And when you count all the red dots, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49. And therefore, in a non-scientific way, we got the answer, which is A for number 25. The number 5 to the power of 867 is between 2 to the power of 2013 and 2 to the power of 2014. How many pairs of integers mn are there such that 1 is less than m is less than 2012, and 5 to the power of n is less than 2 to the power of m, less than 2 to the power of m plus 2, less than 5 to the power of n plus 1? Before we tackle this question, let's try to understand it. And let's understand it with the very basics. Let's start with n equals 1, 2, 3, like that, and m equals 1, 2, 3. So if we do, I'll write the powers of 5 to the power of 1, 5 to the power of 2. I'll just write a few. 5 to the power of 3, 5 to the power of 4. I think that's sufficient. And that's, of course, 5, 1, and then 5, and then 25, 125, and of course 625. Now, in between those, to try to look like that, I'm going to write powers of 2. So I've got 2, 4, 8, 16, 32, 64, 128, 256, 512, and so on, right? So this was, of course, 2 to the power of 1, 2 to the power of 2, and so on, 2 to the power of 3, 2 to the power of 4, and obviously you get the picture here. So how do we approach this question? As you can clearly see from this, and hopefully from this, is that we want a situation where a power of 5 is less than 2 powers of 2, but is also less than the power of 5 when you add just 1 to the end. So a simple example, if I look through here, the one that works is this scenario right here. And that means it works for n equals 3 and m equals 7. So for example, 5 to the power of 3 is indeed less than 2 to the power of 7, which is less than 2 to the power of 9, which is less than 5 to the power of n plus 1, which would be 4. As you can see, 5 to the power of 3 is 125. That is indeed less than 128, which is less than 512, and that is, of course, less than 625. So that means this n and m is one possible pair. So one possible pair is mn73. All right? So we have a lot of work, though, because as you can see, the answer choices are far greater than 1. I found 1 so far, but they're talking in the 270s and 280s. But fortunately, we don't have to go through this one by one. That would be extremely time consuming. There's a very nice, elegant way of doing this question. And here we go. And hopefully I don't need much more space than that, since it's a very nice solution. Now you might say, well, I think I understand, but why did they give me that piece of information there? They've given you that to help you. And I'll explain how that helps you. What we really are boiling this down to is we want a situation where 3 powers of 2 are squeezed in between 2 powers of 5, right? Because if you notice, this had only 2 powers of 2 in between 2 powers of 5. Over here, we only have 2 powers of 2 in between 2 powers of 5. And similarly, we only have 2 powers of 2 in between 2 powers of 5. So these, unfortunately, don't help us. They don't give us anything that we can use here. But this one does. And the reason it does, because we have 3 powers of 2 in between 2 powers of 5. And that is the type of situation we want. So that is what we're going to do. So what we are going to do is let x represent the number of intervals that have 2 powers of 2. So this is one such, this is another such, this is another such interval. And let y be the number of intervals with 3 powers of 2. So that would be basically this scenario right here. Now, how many intervals am I going to count, though? So far, I've got 1, 2, and 3. So I've got 3 intervals that have 2 powers of 2. And I've only listed one here that has 3 powers of 2. Well, that's where this comes in. That clue is very, very helpful. And here is why it's helpful. Basically, what they're saying is that 2 to the power of 213, 2013 is less than 5 to the power of 867 is less than 2 to the power of 2014. Correct? So this helpful inequality that they gave us in the question stem tells us that the 867 intervals between powers of 5 have a total of 2013 powers of 2. Now, if you say, I'm not really getting that, no problem. I'll explain it to you a little further. And I'll explain it with this simple explanation right here. Let's say, from this, I wrote that 5 to the power of 4 is greater than 2 to the power of 9. Well, that's definitely true. As you can see, 2 to the power of 9 is 512, and 5 to the power of 4 is 625. So that would definitely be accurate. From that, hopefully you can deduce something similar as that. That tells us that there are 4 intervals between powers of 5. So to repeat, it tells us that there are 4 intervals between powers of 5. Just look at it. Here's the first interval, second, third, and fourth. There are 4 intervals between powers of 5. And in those intervals, we have how many powers of 2? Well, we've got 9 of them. 1, 2, 3, 4, 5, 6, 7, 8, 9. And therefore, those intervals contain 9 powers of 2. So, from this, we can explain it very easily since it's right there in front of us. But for this, of course, we're certainly not going to write it all out. So we have to sort of envision that, interpret it. And that's what this is. All right, great. So now we're down to the final step of the question. And remember, we let x be the number of intervals that have 2 powers of 2, so something like this. And we let y be the number of intervals that have 3 powers of 2, so something like that. Well, we know a few things. We know that the number of intervals that qualify as x and the number of intervals that qualify as y, if you add them up, it's going to equal the total number of intervals, which is 867. That's the first piece of information. That's the number of intervals. And then, if you take x and multiply by 2, and then you take y and multiply by 3, that's going to give you the number of powers of 2, right? Because when you add them up, it essentially is the powers of 2 that you're adding up. And that is equal to 2013. So if you can understand up until here, you're all set. Because at this point, you're just have to solving this basic system of equations, 2 variables, 2 equations. So here we go. This is going to give me just x is equal to 867 minus y. Sub that into here. And we get 867 minus y plus 3y is equal to 2013. So this is going to be 1734 minus 2y plus 3y is equal to 2013. And then collecting like terms, this becomes y is equal to 279. And that represents the number of intervals with 3 powers of 2, and that is the only way we can get this original equation to work right here, as I had hopefully explained in detail right there. We need to have an interval that has 3 powers of 2, like here, in between 2 powers of 5. And the number of such intervals we have calculated to be 279. So that is the answer to this question. Number 25 is B. Let S be a square of side length 1. 2 points are chosen independently at random on the sides of S. The probability that the straight line distance between the points is at least 1/2 is a minus b pi over c, where a, b, and c are positive integers, and the greatest common denominator of a, b, and c is equal to 1. What is a plus b plus c? And greatest common divisor, that is. All right, well, we've got a few scenarios here. The first one is, I'll just draw them out. We've got 1 square, we've got another square, and we've got a third square. Now, the first one is a scenario where the 2 points are on opposite sides. So we choose a point here, and then we choose a point on the opposite side. Now, when we draw a line between those 2 points, I hope you can clearly see that it's always going to be greater than a half. It's actually going to be greater than a 1, because this square has side lengths 1 and 1 all the way around. So if I have a point here and a point here, even if I have them completely opposite each other like that, and I draw a line, the minimum distance is going to be 1. And if I draw a line on a slant, it's always going to be greater than 1. So the probability that that distance between those 2 points is greater than a half and I'll label that D here. The probability of D being greater than or equal to a half, which is what the question is saying, at least 1/2 is 1. So that's pretty straightforward. And this scenario, this first scenario, happens 1/4 of the time, right? If you choose a point here, the second point can be either here, 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 or here. But I put the second point on the opposite side here, so that's 1 out of 4. So this happens 1 out of 4 of the time, of the total. All right, so that's the first scenario. The second scenario is when both of the points are on the same side. So for example, this is one point and this is a second point. And we want the distance to be greater than or equal to a half. So points are on the same side. And we have to figure out what is the probability that that distance is greater than or equal to a half. Well, that's going to happen basically if there's a couple scenarios. Let's say I call this guy A and I call this guy B. Well, clearly for this line AB to be greater than a half, B has to be greater than A plus a half. Right? If A, for example, was 0, let's say this represents 0, then B's got to be at least a half. If B was, say, if A was, say, here, which is 0 point whatever, 2, let's say, then B's got to be at least 0.7. See what I mean? So that's where we get this inequality. Another inequality is the opposite. If we reverse the conditions, we could have them as B less than or equal to A minus a half. So for example, if we reverse them, so I put A here, they're on the same side, and B is here, and A, say, is 0.8, then B has to be less than or equal to 0.8 minus a half, which is 0.5. So B has to be less than or equal to, what's that, 0.3? So B has to be less than or equal to 0.3, so let's say it's 0.2. And that indeed would make the distance from A to B greater than or equal to a half. So those are the two inequalities that must hold true. Now those two inequalities, we have to graph them. And when we graph them, it will be a scenario where we can figure out the probability. So if I graph these now, I'll just make a square here where this represents A and this represents B. So this right here, B is greater than or equal to A plus a half, is essentially the midpoints, the line between those two midpoints. So like this. And then the other one where B is less than or equal to A minus a half is the line between those two midpoints. So this scenario right here. And the area of those two represent the probability. So this whole thing was 1, so this is a half, this is a half. So the area pretty much is 2 times those two triangles, and each of those triangles is 1/2 base times height, where the base and the height are both a half. So this is a quarter when you multiply it all out. So this probability in here is a quarter right there. Okay, and this happens, this scenario happens 1/4 of the time of the total. Right, because if you put something on one side, you have 4 possible choices for the second point. You can either put it here, 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 or here. I've chosen to put it on the same side, so there's only one out of the 4 possible places. So that's why it's 1 out of 4. All right, now we get to the last part. And the last part is when the points are on adjacent sides. So for example, one point is here and another point is here. And I've got to make sure that the distance between those 2 points is at least a half. So if this is A and this is B, I've got to make sure that distance is at least a half. So the probability of that, of D being greater than a half, is what I have to now figure out. All right, well, if this is A and this is B, and this is obviously a right angle, I can use Pythagoras. A squared plus B squared is equal to 1/2 squared. So A squared plus B squared is equal to a quarter. But how am I going to graph that now? I was able to graph it on the previous one pretty easily, but now what's this? Well, I hope you can recognize that this here is really the equation of a circle. It's the circle where A and B are obviously between 0 and 1. So we're only looking at the first quadrant where this is A and this is B. And the radius of the circle is a half. So first let's draw in our boundaries, which would be 1 and 1. And then we have to draw in a circle that has a radius of a half. So something like that. And we want the probability as follows. We want anything that is equal to a half, but also what's going to be perfectly valid is if it's greater than a half. For example, if I'd made a line like this, or if I made a line like that, that's fine. So really what we want is A plus B is not just equal, but it's actually equal to or greater than. So it's like this. Now on this graph, if A plus B was equal to a half, it'd be just that line right there, that part of the circumference. But it's greater than, so it's basically this whole region right here. And that is the area we have to figure out. Well, that area will be as follows. I'll do it over here. So now we have to combine our findings. Our probability will be this 1/4 times this 1 plus this 1/4 times this 1/4 plus this half times this 1 minus pi over 16. So now if we combine, we get a quarter plus 1 over 16. Multiplying this out, we get 1/2 minus pi over 32. Get a common denominator. It'll be all over 32. This will be 8 plus 2 plus 16 minus pi. This becomes 26 minus pi over 32. And that is of the form A minus b times pi over c. So that means my a is 26, my b is 1, and my c is 32. Greatest common divisor of 26, 1, and 32 is indeed 1. So now all I have to do is figure out the sum, a plus b plus c, and that is 26 plus 1 plus 32, which is equal to 59. So 59 is the answer to this question, and that would mean 25. The answer is A. How many ordered triples xyz of positive integers satisfy LCM xy is 72, LCM xz is 600, and LCM of yz is 900? We are given a few clues. Lowest common multiple or least common multiple, whichever way you'd like to say it, is 72. So I'm going to break this up into its prime factors. I think that will be most helpful for us. 72 is what? 2 to the power of 3 times 3 squared. All right, moving in the same way, the next one is xz, and that's 600. So that means LCM of xz is the prime factor of 600 would be 2 to the power of 3 times 3 to the power of 1 times 5 to the power of 2. And then the LCM of the next one is yz, and that's 900. So breaking that up into prime factors, we would get 2 to the power of 2, 3 to the power of 2, and 5 to the power of 2. Okay. So what I'm going to do is use some triangles to kind of illustrate all this. I hope it helps. So if you have x, y, and z, let's see what we get. Well, x and y have a least common multiple of 2 to the power of 3, 3 to the power of 2. And then x and z, 2 to the power of 3, 3 to the power of 1, and 5 to the power of 2. And y and z are 2 to the power of 2, 3 to the power of 2, and 5 to the power of 2 with regard to their least common multiples. All right, so now what we want to do is take a look at this one prime number at a time. So first, let's just start off with the 2's. And we'll then talk about 3's, and then at the end we'll talk about the 5's. So let's just look at the 2's. Well, it's 2 to the power of 3 here, 2 to the power of 3 here, and 2 to the power of 2 here. 2 to the power of 3, 2 to the power of 3, 2 to the power of 2. Okay, so that obviously means that x has a 2 to the power of 3 as part of its factors. It might be entirely equal to 2 to the power of 3, or it might have 2 to the power of 3 as part of its factorization. But regardless, it definitely has 2 to the power of 3. So now I've got to figure out what is y and z. Well, they have a LCM of 2 to the power of 2. So I've got a few choices here. It could be 2 to the power of 0 for y and 2 to the power of 2 for z. Or it could be 2 to the power of 1 and 2 to the power of 2. Or it could be 2 to the power of 2 and 2 to the power of 2, 2 to the power of 2, 2 to the power of 1, or 2 to the power of 2 and 2 to the power of 0. Any of these would satisfy y and z having an LCM of 2 to the power of 2. And as you can see, there's 5 such ways of arranging y and z, or creating y and z. All right, so now that's pretty good. Let's move on to the next one. The next one will be talking about 3's. So here's x, here's y, and here's z. And now I've got to put 3 to the power of 2, 3 to the power of 1, and 3 to the power of 2, like that. So 3 to the power of 2, 3 to the power of 2, and 3 to the power of 1. So obviously y is equal to 3 to the power of 2, meaning 3 to the power of 2 is part of y. That's pretty obvious. Now I've got to figure out x and y. Well, x and y, a few choices, right? We can have either 3 to the power of 1 for x, and z could be 3 to the power of 1 also. Or you can have 3 to the power of 0 for x, and 3 to the power of 1. Or you can have 3 to the power of 1 here and 3 to the power of 0 here. I think those are the ones that would be the only ones. Yeah. So that means this combined with this gives me 3 possibilities. 3 arrangements for x and y. Either this guy with this guy with this guy, or the 3 to the power of 1 with 3 to the power of 0. So that's 3. Okay, so I think I'm getting close here. One final triangle, of course, and that's got to look at the 5s. So let's look at the 5s now. So here we go. X, Y, and Z. And let's see if I refresh my memory here. There was no 5 here, 5 to the 2 and 5 to the 2. Okay, so that means 5 to the power of 0, 5 to the power of 2, and 5 to the power of 2. So that means Z must be my 5 to the power of 2. And then the combinations for X and Y, X can be, well, there's only one choice, 5 to the power of 0, and Y, 5 to the power of 0 for X and Y, these two. That's it. So that means I've only got one possible way of setting up X and Y with regard to powers of 5. Okay, so I'm ready to figure out the total number of cases. 5 number of cases for the 2's, multiply that by 3 cases for the powers of 3, and multiply that by the 1 case for powers of 5. And 5 times 3 times 1, of course, is 15. And that is the total number of ordered triples, x, y, z, that satisfy the conditions of the question. So number 25, the answer is A. How many integers between 100 and 999 inclusive have the property that some permutation of its digits is a multiple of 11 between 100 and 999? For example, both 121 and 211 have this property. Well, we have 999 numbers, and we have to divide that by 11, take the integer value, and subtract from it 99, that's just below 100, and subtract that divided by 11. And that will give you the number of integers that are divisible by 11. And this is 90 minus 9, so it's 81. 81 are divisible by 11 between that range inclusive. But each of those will give permutations. Some will give 6 permutations, some will give 4 permutations, and so on. So we have to do some casework to figure out how this will all work out. Well, there's one rule that will be very helpful. Any number of the form A, B, C will be divisible by 11 if and only if A minus B plus C is divisible by 11. So, for example, if we have 2, 2, and 0, that would be divisible by 11 because 2 minus 2 plus 0 is 0, and 0 is divisible by 11, right? It's 0. So we have to take that rule into consideration. So case number 1 are any numbers that are of the form A, and then 0, where A is any digit between 1 and 9 inclusive. And as you can clearly see, there's 9 of these. So there's 9 such numbers. And once we have identified those 9 numbers, we have to figure out the permutations. So each of these can be permuted to give the following. A0A. For example, if the number was 110, a permutation would be 101. You can't put the 0 in the first digit because that would no longer be a number greater than 100. So Each of these gives one permutation. There's 9 numbers, 9 additional permutations. So 9 plus 9, 18. That is how many we get here. All right, next case is when we have numbers of the form A, B, A, like that. And in this case, A minus B plus A has got to be divisible by 11. This is 2A minus B. And we have 8 such numbers. And those numbers, I'll just write them out. 1, 2, 1, 2, 4, 2, 3, 6, 3, 4, 8, 4, 5, not 5, but 6, 1, 6, 7, 3, 7, 8, 5, 8, and 7, 7, 9. And these 8, again, each of them can be permuted to form 3 numbers. So, for example, 1, 2, 1 can be permuted to 1, 1, 2, and 2, 1, 1. So there's 1, 2, 3, as you can see, numbers for each of those 3 permutations. And therefore, we had 8. They can form 3 each, so 8 times 3 is the total, which is 24. So we got 24 here. Now we get to the next case, which is when the numbers are of the form A, 0, and C. Here, using our formula right here, we get that A minus 0 plus C is divisible by 11. So, keeping that in mind, we can come up with another 8 such numbers. And those are 2, 0, 9, because this is essentially just A plus C. So 2 numbers, A plus C, that add up to get divisible by 11, 3, 0, 8, 4, 0, 7, 5, 0, 6, 6, 0, 5, 7, 0, 4, 8, 0, 3, and 9, 0, 2. And each of these can be permuted to form 4 numbers. For example, the 209 could be 209, 290, 920, or 902. So we have 8. Each can form 4 permutations, so 8 times 4 is 32. But here's the thing. This is where things get tricky. We have overcounted with that 32. Why? Because look at 902. 902's permutations are 902, 920, 290, and 209. And these are the exact same as these guys. So similarly, this and this would give the same. This and this would give the same. And this would give the same. So this number 32 has to be divided by 2 since we double counted. So 16 is the answer in terms of unique permutations. And now we are down to the last step, where the original 81 that we had here, so far of those original 81, we have talked about these 9, these 8, and these 8. So we got to take those away and talk about the remaining, I should say. So those are 56 remaining. Those 56 we haven't talked about yet. And each of those can be permuted in 6 ways. And the reason is these 56 are of the form A, B, C. They have 3 different digits, so they can have 6 permutations. So I got 56 times 6, which is 336. Now we have 56 times 6, 56 numbers, and each of them gives 6 permutations, so 336. However, in each case, both ABC and CBA, and only these, are multiples of 11. So a perfect example of that would be, say, something like 132 and 231. That is ABC and that's CBA, this one and this one respectively. And these 56 multiples of 11 therefore give only 28 distinct sets of permutations, because each of these would give the same 6 permutations, right? 132, it would be 132 itself, 123, 312, 321, 213, and 231. 231 would give the exact same. 231, 213, 321, 312, 123, and 132. So what we have to do is we have to take this number and divide it by 2. So therefore, we have only 28 times 6, which is 168 integers with the required property. So that is the number we are going to use. So let's add all this up. This 168 right here, plus this 16, plus this 24, plus this 18. So that is 168 plus 16 plus 24 plus 18, and that is 226. Therefore, the answer to number 25 is A. For a positive integer n and non-zero digits a, b, and c, let a n be the n-digit integer, each of whose digits is equal to a. Let bn be the n-digit integer, each of whose digits is equal to b. And let cn be the 2n-digit, not n-digit, integer, each of whose digits is equal to c. What is the greatest possible value of a plus b plus c, for which there are at least 2 values of n, such that cn minus bn is equal to an squared? First, let's start off with a simple example to kind of illustrate what this question is talking about. Let's say n is 3, and therefore a would be 3 digits, and all the digits are equal to a. So it would be a. Similarly, b would be 3 digits with all being b. c, however, is 2n digits, so 6 digits with all its digits being c, like this. And they're basically saying when you do that, this has got to hold true. So this is, of course, C3, B3, and A3. So they're saying that whatever happens, once you get these numbers, you plug them in, and this holds true for 2 values of n. So I'm just going to give you an example. Let's say b is equal to 5. Okay, this is just an example. That means b3 is 5, 5, 5, right? So the trick to this question is trying to figure out a very cool way of manipulating these numbers. So 5, 5, 5, I'm going to write as follows. If you divide this by 5, obviously, you would get 1, 1, 1. Now, what is 1, 1, 1? I like the 5. I'll keep that. 1, 1, 1 is really 9, 9, 9 divided by 9. And 9, 9, 9 is really 10 to the power of 3 minus 1. So this is basically what we want to do. We want to take the number and put it in this form. That's challenging. I understand. So in general, if we were to sort of make a general formula, it would be that bn would be b times 10 to the power of n minus 1 over 9. If you notice, this one, of course, I had given specific values for n and for b. But in this one, this is general. N is just n and b is just b. Okay, so now we can go to the question. Now that we have a strategy. So let's look at that one. So we've got c to the n minus b to the n is equal to a to the n all squared. C to the n would be, according to this formula, c times 10 to the power of 2n minus 1 over 9. b to the n is b times 10 to the power of n minus 1 over 9. And then a to the n is a times 10 to the n minus 1 over 9 all squared. Correct? All right. So if you're convinced of that, let's move forward here. So at this point, let's do a little bit of expansion, not too much. C 10 to the n minus 1 and 10 to the n plus 1, and that's going to be over 9. B, this is just going to be pretty much the same thing. Not much I can do there. This one, a squared 10 to the n minus 1 all squared. And then 9, don't forget to square that one. It's going to be 81. Now at this point, we can divide by 10 to the n minus 1 because that appears with everything. And when I do, it's going to be c to the 9, just one of these 10 to the n plus 1, because 10 to the n minus 1 will disappear. And then from here, it'll be just b over 9 because the 10 to the n minus 1 disappears. And then here it'll be a squared over 81, and then just one of those will remain, 10 to the n minus 1. Okay. Now let's multiply through by 81 to get rid of the fractions, and when we do, we get 9c 10 to the n plus 1 minus 9b, and then a squared 10 to the n minus 1. Okay, so we're making some progress here. At this point, we want to expand and collect like terms as best as we can. So let's do that. This is going to be 9c 10 to the n plus 9c minus 9b is equal to a squared 10 to the n minus a squared. Let's put the 10 to the n's on one side and factor. When you do, you get 9c minus a squared. And then we have 9 on the other side. If I put everything else on the other side, it would be 9b minus 9c, and I believe just alone minus a squared. Okay, great. Now, here is the part of the question. This must hold true for two different values of n. And we can call those n1 and n2. So basically it means that 9c minus a squared times 10 to the n1 is going to be 9b minus 9c minus a squared. And 9c minus a squared to the 10 to the power of n2 is also going to be equal to 9b minus 9c minus a squared, right? Because both of them have to be equivalent. You're going to have this equation holding true for two values of n. So I'll call those equations 1 and 2. And then at this point, what I'm going to do is subtract them. 1 minus 2. So 1 minus 2 would give me 9c minus a squared 10 to the n1 minus 10 to the n2. And on the other side, it basically becomes 0. Okay. So the only way this is going to work is if this is equal to 0. Because this can't be 0 because n1 and n2 are two different numbers. So that means I conclude that 9c minus a squared is equal to 0. And if that is the case, and you plug that back into 1, then the left side becomes 0. So that means this is equal to 0. So that 9b minus 9c minus a squared is 0. And these two will help us solve for a, b, and c, I hope. From this one, we get 9c is equal to a squared, and therefore c is equal to a squared over 9, which is a over 3 all squared. From this one, let's see what we can get here. we get 9b minus 9c minus a squared. So 9c is equal to a squared, this guy, so I can just put a squared minus a squared is equal to 0. So that means 9b is equal to 2a squared. And 9b, therefore, a squared is 9c, so 2 times 9c, right, from this right here. So that means b is equal to 2c. Yeah, that's it. Okay, so now I think we're ready to figure out a, b, and c. A, b, and c. Well, from here, these are all integers, so a obviously is divisible by 3. So a can only be either 3, 6, or 9, because remember, each of those are digits, so they're only between 1 and 9. If a is 3, I think I can immediately figure out c. So if a was 3, c would be 1. If a was 6, c would be 4. And a was 9, c would be 9 also. Okay, now let's figure out the corresponding values of b using that formula. b is just 2 times c, so 2, 8, and 18. Well, this one is invalid because b has to be a digit, right? So this one here, that doesn't work. So I guess the only ones that work are that ordered triple and that ordered triple. So now we have to figure out the value of a plus b plus c. Okay, from this guy right here, a plus b plus c is 6. And from this one, it is 18. And we have to choose the largest. So the largest obviously is 18. And therefore, going back, what is the greatest possible value of a plus b plus c, for which there are at least 2 values of n such that cn minus bn is equal to an squared? We just figured out that answer is 18. And therefore, number 25, the answer is D. For how many integers n between 1 and 50 inclusive is n squared minus 1 factorial over n factorial to the power of n an integer? Recall that 0 factorial is equal to 1. Well, let's think about this for a second. Before I dive into this, I just want to mention, if you had n factorial over, say, n squared, well, you could write this as n times n minus 1 factorial, and then the bottom you can break up into n times n. These two n's would cancel, and it would leave you with just n minus 1 factorial over n. So with that in mind, now let's tackle this guy. So that is step 2, n squared minus 1 factorial over n factorial to the power of n. Now for this, I want to make this into a better form. So what I'm going to do is I'm actually going to introduce a couple of things here. I'm going to keep what we have, of course, but then I'm going to introduce an n squared on the top and the bottom like that. When I do that, you'll notice that the top now becomes n squared factorial, very similar to what I did up top. And then the bottom now, we have this n factorial to the power of n times n squared. Okay, I'd like to work with this a little bit more. And the way I'm going to do that is by, again, adding n factorial to the top and bottom. And that will allow me to make a couple more changes. The first change is that I will just combine this one and this one to give me n factorial n plus 1, and then I'll just rearrange that n factorial and put it over n squared, and then this n squared factorial will remain the same. Okay, so now we want this to be an integer. Now, notice that if you just look at this term, that n squared factorial is going to be much greater than n factorial to the power of n plus 1. For example, if you had, say, n is equal to, say, 15, well, this part becomes 15 squared factorial, which is 225 factorial. And that's obviously going to be much greater than 15 factorial to the power of 16. So I'm fairly confident that this part will be an integer since the numerator is greater than the denominator. So now I have to concentrate on that. And that is the key to the question right here. I've got to concentrate on this guy. So I want that to be an integer. Well, let's see what happens. Remember, my range is from 1 to 50 for n. So let's see what happens with the first few. When n is 1, we get 1. When n is 2, we get 2 over 4. When n is 3, we get 6 over 9. When n is 4, we get 24 over 16. When n is 5, 5 is interesting because I think it's a little bit clearer that when it's a prime number like 5, it'll be 5 factorial over 5 squared, which is 5 times 5. And there's no way that this is going to be an integer because this 5 could cancel out with the first 5, right? But then there's no other 5 in the rest of the factorial, 4 times 3 times 2. So this is not going to be an integer. That's not going to work. How about n equals 6? That is going to be 6 factorial over 36. And that actually gives me 120. And you can keep going like this. And when you do, you hopefully will come to a conclusion that this n factorial over n squared is an integer when n is equal to 1, like we showed here, or n is not equal to 4, right? Because 4 didn't give me a value that works. Or n is not a prime, because for prime numbers it won't work. So basically, all the numbers between 1 and 50 that need to be eliminated are the primes and the 4. So that's pretty much how we're going to do this. So of the 50 numbers between 1 and 50, we get rid of that 4, so that's just one number, that 4. And then everything else that we get rid of is a prime number. And between 1 and 50, if you count them, there are 15 prime numbers. So 50 minus 1 minus 15 is 34. So 34 values of n between 1 and 50 will give this to be an integer, and therefore that whole thing will be an integer because it essentially was a modification of the original formula. And therefore number 25, the answer is D. Jason rolls 3 fair standard 6-sided dice. Then he looks at the rolls and chooses a subset of the dice, possibly empty, possibly all 3 dice, to re-roll. After re-rolling, he wins if and only if the sum of the numbers face up on the 3 dice is exactly 7. Jason always plays to optimize his chances of winning. What is the probability that he chooses to re-roll exactly 2 of the dice? On his initial roll, he will have 3 numbers. And we want to see how we can get a sum of 7. Well, 511 would do it, and there's going to be 3 permutations of that. I'm not going to write out all the permutations. I assume you know how to do that. You can also have 421. That gives me 6 permutations. 3, 3, 1, that also gives a sum of 7. 3 permutations of that. And 3, 2, 2, that has 3 permutations. So in total, I've got 15 ways of getting a sum of 7 when 3 dice are rolled. Now, what is the total number? Because I want to get the probability. 15 is the numerator, but what's the denominator? For each of those 3, I have 6 possible outcomes, 1 through 6. So the total would be 6 possible choices for the first, 6 possible choices for the second, and 6 choices for the third. So that's 216. So that is the denominator. In lowest terms, that's 5 over 72. So this is the probability of him winning when he just rolls 3 dice. And that's it. He doesn't go any further. All right, so now the question is asking us something very specific. It's saying, what is the probability that he chooses to re-roll exactly 2 of the dice? So I'll give you a scenario. Let's say we have an initial roll, and we rolled 3 numbers. And one of them, we'll just start with the number 1. The first dice had a 1 on it. And the other 2, we don't know, but we know that he didn't roll a 7. Okay. Then he's going to pick up this dice and roll it again. So the number of dice that he re-rolls is 2. Exactly 2. If he does, what is the sum of those dice in order to win? Well, the sum has to be 7 for all 3. We already got a 1, so the sum has to be 6. So how do you get a 6? Well, you can get a 6 in a few ways. You can get either a 5 and a 1 and a 5. You can get a 4 and a 2 and a 4, or 3 and a 3. Yeah, 3 and a 3. So as you can clearly see, there's 5 ways of winning these 5. So 5, the probability, over 36. Why 36? Because the first dice, there's 6 possible choices, 6 possible outcomes. And for the second dice there's also 6 possible outcomes. So that's why you get that 36 there. And of those 36, 5 would make him win. All right, so that's an important number. How about if you had an initial roll and you had 2 as the first number, and then he didn't get 7, but he wanted to re-roll these 2. Same thing, you need a 6, so you only get, you need a 5, because 5 plus 2 is 7. So how can you get a 5? Well, 1 and a 4, 4 and a 1, 3 and a 2, or 2 and a 3. So as you can see, there's 4 ways of the 36 possible outcomes when 2 dice are rolled. And let's just put that 2 there. How about if I have a 3? Well, this sum has to be 4 now, because 4 plus 3 is 7. And how do I get a 4? Well, either a 1 or a 3 or a 1, or a 2 and a 2. So there's, as you can see, 3 ways, these 3, out of the 36 possible ways, outcomes, when 2 dice are rolled. Okay, so here's the part of the question that I think is challenging. It took me a while to really understand this. Here's the thing. If he rolls 3 dice, so we're talking about this situation, right? And he gets a 7, he wins the game. All right, no need to do anything else. If he rolls 3 dice and he doesn't get a 7, he obviously needs to roll again. Now, if he needs to roll at least 2 dice, which is our scenario here, then he re-rolls them only if the probability of winning, which are these probabilities, is greater than this. So let me write that out. If he needs to re-roll 2 dice, this situation, to win, he re-rolls 2 dice if, and only if the probability of winning is greater than 5 over 72. If it's not, then what he'll do is he'll just pick up the 3 dice and roll them again, because that gives him a better chance of winning. So if you continue this table, I wanted to stop and explain it. If this is a 4 and you go through the same thing, you will get a probability of 2 over 36. And if this is a 5 and you go through the same thing, you'll get a probability of just 1 over 36. Now, which one of these probabilities is greater than 5 over 72? It has to be greater than 5 over 72. Otherwise, it doesn't make any sense for him to re-roll 2 dice. He can just re-roll 3 dice, because 5 over 72 would have been the better probability. Well, I'll tell you. What we can do is let's put them over the same denominator. It makes it easier to compare. This is 10 over 72. This is 8 over 72. This is 6 over 72. This is 4 over 72. And this is 2 over 72. Which one of those is greater than 5 over 72? Well, obviously, these ones. These scenarios. This is not, and this is not. So, let's explain again. If he needs to re-roll 2 dice, he re-rolls 2 dice if and only if the probability of winning is greater than 5 over 72, which is this guy, and this guy. For here, he will not do that. He will re-roll 3 dice, because if he re-rolls 3 dice, the chance of winning is 5 over 72. That's a better probability than if he does this, which is only 4 over 72. He obviously wants to optimize his chances of winning. All right, so I think I've beaten that to death. Now let's move on. So we have to just look at this, this, and this. Okay, so if he has 1 as the first number, then he says, okay, I've got 1 as my first number. I want to win. How do I win? 1 as my first number. Now he's got to think, what do I do here? Do I pick up the 2 dice and roll again? Well, it seems like the right thing to do, but he has to think about the second number. The second number is going to really make him decide. Let's say the second number is 2. Well, now that third number has to be very specific. It has to be a 4 in order for him to win. And he, therefore, has to understand that this third number, if it's not a 4, so not 4, he obviously has to roll again. So now he's got a choice. What do I do? Do I pick up all 3 and roll again in order to win? Well, if he does, there's a 5 over 72 chance right here. Do I pick up only 2 and roll again? Well, we just calculated there's a 10 over 72 chance. Do I just pick up 1 and roll again? I just pick that up and roll again, and hopefully it'll be a 4. Well, 1 over 6 chance of getting a 4, and if you put that over 72, get a common denominator is 12 over 72. So of these, which is the highest? He wants to maximize his probability of winning. The highest of these is obviously this guy. So he's just going to pick up this and roll again. He's not going to pick up 2. And similarly, the same story is if you have a 1 and a 3, and then a not 4, a 1 and a 4, a 1 and a 5, you will have the exact same story. He will just pick up the third one and roll again. The only time he's going to pick up 2 is if you have 1 and then a 6 and a not 4. But that not 4 also cannot be a 1, because then you just have the same scenario. So it has to be a 1, 1, and a 6. Any other scenario would actually be very similar to this. And I don't want to keep drilling this home, but for example, if I had a 1 and a 6 and then a 1, well, that's very similar to this right here. It's just one different. All I have to do is pick this up and roll again. So we want a scenario where he absolutely must pick up 2 in order to win, and that is going to happen in that scenario. 166, he has to pick up those 2 6s and roll again. And there's 3 permutations of that. 166, 616, and 661. All right, so hopefully that makes sense. Now let's move on to what other scenarios we have. The other scenario is if you have 2 as the first number, which is our next guy right here. 2 is our first number. And then, again, I'm not going to beat this home like I did with the first one, but I'll just give you the scenarios. The next 2 numbers, it has to be either a 5 over a 6 or a 5 over a 6. So the possible choices are 255, 266, or 256. There's 3 permutations here, 3 permutations here, and 6. So this gives me 12. So 12 in total. And then finally, we have this guy, 3. That has a probability of 6 over 72. But let me just compare the probabilities for this before I jump ahead. The probability of him picking up 2 and winning is 8 over 72, right? If he were to pick up all 3 and roll again, the probability of him winning is 5 over 72. And if he picks up just 1 and rolls again, let's say he picks up that 1, he will definitely not win because 2 plus 5 is already 7. So if he picks up 1 and rolls again, he's always going to get a sum of more than 7, so 0. So obviously of those 3 numbers, the highest is 8 over 72. So I just wanted to justify how the picking up 2 and rolling again is going to optimize his chances of winning. And now we have just one final scenario, and that is this guy. That's when you have the 3. And again, I'm not going to go through all the choices. I'm just going to list the ones that are correct. The first number is fixed as 3. The next 2 can be either 456 or 456. And that has the following permutations: either 344, 355, 366, or 345, 346, or 356. And there's 3 permutations here, 3 here, 3 here, 6, 6, and 6. So that is 18 plus 9, 27. And again, let's just review the probabilities. If he picks up 2 and rolls again, the probability of him winning is 6 over 72. If he picks up all 3 and rolls again, the probability of him winning is 5 over 72. If he picks up just 1 and rolls again, the probability of him winning is 0, because 3 and any of these numbers already adds up to more than 7. So if he picked up the 3rd and rolled again, he's never going to get a sum of 7 for all 3. And obviously of these, the highest probability and therefore optimizing his chances of winning is the 6 over 72, which is this scenario, which involves picking up and re-rolling 2 dice. All right, so now we're almost done. We have to add up these values, the 3, the 12, and this 27. So 3 plus 12 plus 27. And remember, it's a probability. The denominator is all the possible choices. And we had previously calculated that as 216. So that is what? 42 over 216. And let's see. If you divide top and bottom by 6, it becomes 7 over 36. And 7 over 36 is A for number 25. How many ways are there to place 3 indistinguishable red chips, 3 indistinguishable blue chips, and 3 indistinguishable green chips in the squares of a 3x3 grid so that no 2 chips of the same color are directly adjacent to each other, either vertically or horizontally? Well, I think a diagram will be very beneficial. So here we go. So first, let's just concentrate on the red chips, and then we'll talk about the blue and the green. So the red chips, these are the possible configurations that you can put them in order to satisfy the condition of the question, which is that no 2 chips of the same color are directly adjacent to each other, either vertically or horizontally. And as you can see, that is satisfied. Now, for this one, there's 2 configurations. Why? Because you can also put them in this corner and that corner. So that would be why it's 2 configuration. With this one, you can just switch the corners. So right now we have this one and this one, but you could put this one and this one as the corners, or this and this, or this and this. That would be 4. For this one, 4 configurations. Right now we have this box there, but it could be there or there or there. So that's 4. In a very similar way, that has 4 configurations. Just look at the corner, right? The corner could be here or here or here. You're just rotating it, I guess. And then the same thing here. This could be either here or here or here. So that takes care of the red. But what about the blue and the green? Well, let's just talk about one such configuration. Let's say I've got this one here, and I am going to use the first configuration, the first one. I'm going to put red here like that. Now, where does the blue and green go? I can put blue here, but then I can't put blue here or here because that would break the rule. So I got to turn my attention and put blue there and then blue there. And then the greens obviously would go in the remaining 3 places. So that is one way of putting the blue and the green. But the good news is that there's only one other way of putting the blue and the green. So if the reds are placed in that kind of diagonal, red, red, red like that, the only other way to putting the blue and the green is by putting blue, blue, and then blue in the corner, and then green would go in the other 3. So for each of these configurations, there's 2 ways that you can put the blue and the green. One like this and one like this. So let's count them all. 2, 4, 4, 4, 4. That is 18. And then for each of those 18, we have to multiply by 2 because you have 2 different ways of putting the blues and the greens. So in total, it's 36. So number 25, the answer is E.